All right, so I can't talk about Kepler without mentioning what a fantastic success it was in doing its primary mission, which was looking for planets. It found, I checked this today, 2,341 confirmed planets. These are not maybe planets. These are like, we know they're real planets. That's a lot of planets. That's half of the known planets to date were discovered by one mission, one mirror. It's incredible. And they built this photometer, this really sensitive digital camera, so that in its position in space, which, mind you, I believe it's in orbit around the sun, not the Earth. So it's actually pretty far from the Earth. If it were looking back at the Earth, it could tell if you were standing in front of your porch light or not. Its brightness measurements are so precise that it could measure very, 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 very small changes in brightness. And let's make that quantitative because we're all scientists here. The measure of brightness that it was looking to measure is something like 20 parts per million of brightness change, which was unfathomable to do before the Kepler mission, because ordinarily you would have a big telescope on the ground and it would try to measure brightness changes, but the Earth's atmosphere is constantly changing and that makes it very difficult to measure these brightness changes. But by going to space and by using a dedicated mission that stared at 150,000 stars for 4 years, taking an image every half hour, we were able to measure these brightness changes at that level of precision to find the Earth-sized planets orbiting sun-like stars. And if it weren't for the fact that people are drawn to planets, we wouldn't have the data set that we're going to use to study stars. And so I always like to pay a little bit of homage to the shiny object, which got us what we're going to make use of, which are the planets, the dullest objects in the universe. So what does Kepler see when it looks at the sky? It sees an image like this. Through Zoom, this might not look like much. And even if you were looking at my screen, it might not look like much. What you see is this weird checkered pattern, which is the field of view of the Kepler instrument. It has a bunch of cameras that are all lined up next to each other. And so if you combine them into a mosaic, this is the chunk of sky that they cover. If we zoom in on just one of these subsets of the image, you can see thousands of stars, many, many, many stars. Some of them are slightly overexposed in this image, and you can see they have elongated tails to the left and right, but most of them aren't. Most of the stars are fairly dim. And that's good news for the Kepler photometer. It's good at measuring brightnesses of dim stars very precisely. What did Kepler do? Well, it's famous for this. It's famous for discovering loads of planets. Blue are all of the previously discovered planets before the Kepler mission. Red were discovered by Kepler. And then in 2014, they published one paper that validated more systems than were previously known. They just did this fantastic amount of work where they found loads and loads of planets very successfully, which is a good sign for us as stellar astrophysicists, because that means they understood all of the bumps and wiggles in their data, which allow us to remove those bumps and wiggles that are systematic and look for the things that are just astrophysical, look for the stars varying. The one-dimensional data set that we're dealing with on each star looks something like this. We call them light curves. They are brightness over time measurements. What Kepler was looking for was the signal of a planet going in front of its star. And we call that event a transit event because the planet transits across the surface of the star. During the transit, the star gets dimmer and then gets brighter again. There's a few features in here that are interesting to talk about, but I'm going to just go through them very briefly, which is the beginning of the transit and the end of the transit are called ingress and egress. If I ever say a term that ends in ESS, what I'm referring to is the beginning or the end of a transit. At the bottom of the transit, which is the deepest point in the light curve, there's a kind of a slow curvature. And that curvature is a real effect of the star. The star is brightest at its center. And you can see this in images of the sun. If you look at the edges of the sun, it looks a little bit darker than at the center of the disk. And that shows up in an exoplanet transit because the planet is blocking a brighter region of the star when it's over the center. And so more light goes missing when the planet's over the center of the star. And what do actual stars look like from the Kepler mission's point of view? Let's look at real data, because that's what we're going to be doing in just a few days. And so let's get our hands dirty a little bit and look at what the real data look like. This is the Kepler time series photometry of a system called Kepler 62. Kepler 62 is the example I'm choosing here because it's a really neat star and planet system. In order to get a name like Kepler dash some number, that system has to have planets. And this system has 5 planets. The 2 outer planets are near the habitable zone of this star. And so this is a really neat system to think about because it's one of the only systems for which we know it has habitable planets that have probably remained habitable throughout the lifetime of the star. We can talk more about that later if you want. There are brightness variations that you see in this light curve. The brightness variations look like small wiggles, like almost as this were a seismograph, right? This kind of looks like an earthquake diagram. Those bumps and wiggles are actually the brightness variations due to rotation of the stellar surface. As spots rotate into and out of view, you get slight brightness increases and decreases. There are also some systematics in here. So there are data gaps, and sometimes the data on either side of the gap don't match up perfectly, and that's systematic. But most of what you're seeing is real. There are positive outliers and negative outliers. The positive outliers are probably not flares. They're probably cosmic ray hits or some other imperfection in the data. The negative outliers probably mostly aren't real as well, but a handful of them are actual transits of planets. They are the brightness dimmings that occur when a planet goes in front of its star. And there are 5 planets in this system, so transits happen pretty frequently in this system. The thing that a stellar astronomer would want to do to this light curve is produce these lower 2 curves. These are curves that you'll see people talk about in the literature, and you'll hear me talk about from time to time, which measure periodicities in the light curve. They look for any signal that looks like a sine wave. The middle panel is called a lone Scargill periodogram. Periodogram is a diagram that shows the amount of sinusoidal power at different periods. And the peak in the periodogram occurs near maybe 13 days for this star, which some people would use to measure the rotation period of the star. Every method of measuring a rotation period for a star is flawed. And so you can't just trust one measurement to tell you the rotation period of the star. Another measurement that people often use is in the bottom panel, which is called the autocorrelation function. If you are a machine learning expert and you're used to thinking about Gaussian processes, then think about the autocorrelation function as like the correlation matrix represented for this data against itself. What you see is this kind of ringing sinusoidal shape that decays out to large lags. I've created the x-axes of the 2 lower plots to be the same. And you can kind of see that there's a peak between 10 and 20 days in the autocorrelation function. And there are a series of peaks between 10 and 20 days in the lone Scargill periodogram. This kind of agreement between the two suggests that the rotation period might be something like that. However, of course, the the one paper that claims a rotation period on this star claims a longer period than either of these periods. And so disagreement in the literature is rampant. There are many reasons for it, and we can discuss them if you want. But what I want to show, yes, Stella.
What is the x-axis, the lag?
In lag. So the way that we plot an autocorrelation function is by measuring the correlation of a data set with itself after displacing the data set by some lag. So in other words, you can kind of shift the data set over itself and measure its correlation. And so a lag of 0 is saying, a lag of 0 is actually a special case, and it measures the standard deviation of your light curve. And then as you move off of lag of 0 to lag of 1, lag of 2, lag of 3, lag of 4, you're measuring slightly different offsets. Here, the lag axis corresponds to essentially the same thing as the axis above it, which is what is the periodic power in units of days. The fundamental units of that plot are actually in cadences, in number of observations that you've moved along, but I've converted it to an axis that makes sense to humans, which would be days.
Yes, thank you. It's clear. Thank you.
Great. So I want to zoom in a little bit on what the data look like. This is the same lower two plots, but a different upper plot. The upper plot is just zoomed in on the x-axis so that you can see what some of the variability of the star looks like up close. And you can see the telltale sign of transits, which are sharp, narrow, negative outliers. If you have a really good eye, you can even see that they're periodic. And that's because the planet's going around once per orbit and comes back and blocks out light again. The other thing that you see is that the brightness is varying and there's some noise about that. The noise is observational in origin. This comes from Poisson statistics because we're counting the number of photons that hit our detector. And so there's a fundamental noise floor on our observations that we just can't overcome. It's due to physics and there's no compromising with it. So unfortunately, no matter how much we smooth our data, that noise floor will always be in there during our observations. And that's part of the difficulty because as you can see, the amplitude of the variability of the star is comparable to the scatter. And so the measurement that we're trying to make is in the margins of the data. Here's another star. The previous star, Kepler 62, is smaller than the sun. Smaller stars, for reasons that we think we understand, but I haven't talked about, are more active than sun-like stars or larger stars. Kepler 452, which is the one plotted here, is a star that's like within 5% of all of the measurements of the sun. It's almost the same radius, almost the same mass, almost the same brightness, almost the same temperature. And you put that all together, and you can see that reflected in the light curve is a smaller amplitude of variability. The y-axis here is the same as the y-axis on the previous plot. And here you can barely see any variability. This, unfortunately, is going to be part of our challenge, which is that sun-like stars have very small variability. The variability that we want to measure is on the scale of the noise. And you can see that reflected in the lower two plots two different ways. In the Lone Scargo periodogram in the middle, you can see that the peak that stands out near maybe 8 days is no longer much higher than the other peaks around it, which speaks to the confidence of that detection, which is a little bit lower. And the same is true of the plot beneath that. The autocorrelation function has multiple peaks, and it's hard to tell which peak is tallest, and there's noise on this curve that you can actually see by eye this time, which was not apparent in the previous plot. So you can use an autoregressive technique to try to measure the period and look for variations in the period. You can use sinusoidal decomposition techniques like the Lone Scargo periodogram. These are what you'll see a lot in the literature. And you could imagine that one of the exercises that we want to do if we want to measure differential rotation is that you would measure the period very precisely. And as spots occur at different latitudes, which correspond to different rotation periods, you would then see that some of the spots go by faster than other spots. And that would be reflected in changes in period in these plots, especially if you were to break up the light curve into chunks and measure the period several times. You might see the period vary a little bit. It turns out that that's really hard to do. For some stars, though, let's look at some Kepler light curves that have really obvious spots, because I want to encourage you to show you that this is at least somewhat possible. We do have some stars that are sun-like, that these are GK and F stars, which have larger amplitudes. The black points here are data, and the blue is a model on the left side, which is the light curve. And you can see that there's this beautiful 1% variability in the upper plot. In the lower plot, there's a slower variability, also at about 1% in amplitude. And you can actually envision what's going on in the lower plot by imagining just a single spot. It looks as though there's one spot that's rolling into view. As you see it come into view, it gets bigger and darker. When it's facing you, the star is at its minimum brightness, and then it rolls away. And as the spot gets smaller, the star gets brighter again. So we can create simple models that predict how big that spot is, where the spot is, and where the companion spots are that give the extra substructure to these light curves. So what I'm showing you here are rough fits. You shouldn't take these as absolute truth, but these are ways that you can reproduce the light curves of Kepler stars using only a handful of spots. In reality, they probably have many more spots than the few that I'm representing here.
Brett, quick question.
Yes.
So when you look at light curves like these, one thing I always wonder is, how do you tell apart stellar spot modulation from pulsations, basically periodic changes in the radius of the star?
Thank you for this question. The short answer is there are some amazing neural nets that have been trained to do this called astronomers. I'm not one of them, but there are some astronomers who basically can pick out by eye, that's a pulsating star, and that is not. The way that they can do it by eye is by knowing a few properties of the star. One is the amplitude of the variability. Another is the period of the variability. And then if you have this information, if you know the mass, radius, and temperature of the star, you can know whether or not you expect the star to pulsate. For those of you who don't know about these radial pulsations, there are stars where there are cyclic changes in the brightness that look kind of like these plots that I'm showing you, except they're due to the fact that the star is actually growing and shrinking on a cycle. And by growing and shrinking and changing its cross-sectional area, it gets brighter and dimmer. And so Tansu's question, which is prescient, is how do I know that the star isn't growing and shrinking in order to produce these brightness variations? The short answer is, if you know the spectral type of the star, if you know its mass and radius and temperature, then you can put it on an HR diagram. And it turns out that all of the stars that pulsate lie in a particular region of the HR diagram. So if you know its temperature, or equivalently its color, and you know its luminosity, then you know whether or not it should pulsate. So these are stars that I've chosen that should not be pulsators. And their periods are consistent with rotation periods of stars, typical for the ages of stars that these stars are expected to be. I think I said stars way too many times in that sentence, sorry. Now, to take away some of the hope that I've given you on this slide, here's what more sun-like stars look like when you look at them with Kepler data. Again, these are both Kepler targets for which planets were discovered orbiting them. But you can see that the variability is on a much finer scale now. We're looking at less than parts per thousand brightness changes. And the noise is obvious this time in the plot where it wasn't before, because the variability of these sun-like stars is so much smaller because their total spot coverage is so much smaller. This is partly a function of age. We know that as stars get older, they have less spots. And that gives us less signal to measure in the rotational modulation of the star. There is a way out of this, though. Imagine with me for a moment that you had a really wacky system that looked like this. You had a Neptune-sized planet that transits a star. When the planet passes over the star, it's going to create brightness variations that we could measure as a transit. Here's what Kepler would see. It's got the normal transit shape, but it also has two bumps in the bottom, or maybe more than two, depending on how you count. Those bumps occur when the planet passes over a dark spot. The reason it gets brighter is because the planet is covering a dark spot of the star, so less light is missing when the planet's on top of the spot than when it's over a bright region on the star. So the curve goes back towards the normal brightness a little bit. We can pull out all kinds of information about the spots that are in these data just using the 1D time series that we have. Because if you know the orientation of the planet on the star, then you can infer, based on the timing of when the spot bump occurs in the light curve, where on the surface of the star the spot was. There's a whole industry devoted to figuring out exactly how the shape of a transit light curve maps onto the orientation of the system. And so we can borrow the exoplanet folks' tools to do that. And once we know the orientation of the planet relative to the star, then we can just back out information about where the spots are, which I said was related to the timing, and how dark the spots are, which is related to the amplitude of those spot occultations. This is what that looks like in real data. This is a system called HAPPY 11, and it is probably my favorite star other than the sun. And I can talk about HAPPY 11 until I turn blue in the face. So I'm going to try to keep this as brief as I can, which is to say that HAPPY 11 is the coolest. It's a star that's 80% the mass of the sun, so 20% less massive. It's got a rotation period of 29 days. If you recall, the sun at the active latitudes, its rotation period is about 26 days. So it's just like the sun with 20% less mass. And when we look at transits of this star, we see these beautiful bumps in the bottom of the transit. There's a lot going on in this plot, but there's the main transit, the U shape, and then two upside down V shapes, or two capital gamma shapes. And those two spikes are the brightness variations due to the planet going over dark spots. I've lined that up with a map on the right side, which represents where the planet actually is in the dark spots, so that you can really visualize the whole system. And this is a Neptune-sized planet orbiting a star, 80% the mass of the sun. Because of this unique system where the planet is actually transiting from near the south pole of its star to near the north pole of the star, which, yes, means the planet's in a polar orbit around this star, which is very different from the solar system. The planet's sweeping out a line across the star at essentially one longitude, but many latitudes. And that's nifty for us because that means our time resolution is latitude resolution in this system. And so where the spots occur in the transit light curve tells us at what latitudes the spots were occurring on the stellar surface. So if you do a bunch of math, where by math I mean you figure out the geometry, which turns out to be horrendously complicated, to create a photometric model that models planets occulting stars, and then stars that have spots on them getting occulted by planets, and you work all that out, which my thesis advisor did, you can create a code that forward models this situation well enough. And then you can run your favorite sampler to investigate the parameter space of spot properties that best fit your light curve. And so on the right, I'm showing you posterior samples from our photometric model, which assumes that spots are circular and that there are 4 of them in this particular transit. You can see that there's degeneracy. Some of the spots could be on the left side of the transit or on the right side of the transit. The spots are smaller if they sit right in the middle of the transit's path, and slightly larger if you're grazing the spot. And so we explore all of that, and we figure out what latitudes we think the spots are at. And to compress my dissertation into a single plot, the latitude distribution of the spots on hat P11 looks kind of like the sun's.
Brad, one
Yes.
question. So this latitude distribution is covariant with the stellar obliquity, right?
Yes.
So I guess normally you have a 2-dimensional distribution. You're showing the marginals here. And have you been able to independently confirm the stellar obliquity using other methods like RM effect?
Yes. Thank you for this question. So we only know the orientation because it was measured through the Rossiter-McLaughlin effect. The Rossiter-McLaughlin effect, which Tansu just mentioned, is this really neat trick that astronomers figured out, which is that if you think about the rotating sun that I showed you in the Doppler image earlier, part of the sun is blue shifted and part of the sun is red shifted because it's rotating. And if you put a planet in front of the star, it's going to block out either the red shifted side or the blue shifted side. And then depending on the path of the planet across the stellar surface will determine the red shifts and blue shifts that are imparted on the star's net radial velocity if you measure it during a transit. And so if you didn't understand any of that, all I want you to take away from that is that during a transit, we can figure out which way the star is spinning relative to the planet's path across it. And so using that information, we can break some degeneracies and figure out which line of longitude and which line of latitudes the planet is blocking during its transit. So another way to say that is that this plot is dependent on that other measurement being correct. And I think to a certain extent, I am fairly confident that it is because we get 2 active latitudes at 15 degrees, which is precisely what the sun would tell us we should expect. There is a degenerate solution, an alternative solution to the Rossiter-McLaughlin observations, which would be that we're observing the star pole on. And there are a few reasons why we don't think that's the case for hat P11. The easiest one to imagine is that the brightness variation of the star is about 3% as it rotates. It would be hard to get 3% variation if you were staring at the pole of the star. It's easier to get that if you're staring at the equator. So because of these 2 lines of evidence, we make the argument that we're just looking equator on at the star, and we're probably seeing 2 active latitudes. So
can I ask you a question?
Yes, please do.
If we combine the candidate stars and the confirmed stars that have planets, I mean, if we treat candidates as if they were actually confirmed planets, how many systems, ballpark, we're talking about? So you said, like, I don't remember the numbers exactly, but it was about 3,000, between 2,000 and 3,000 confirmed planets, but there may be stars that have more than 1 planet. And there were also about the same amount of candidates not confirmed, which will be the same. So if we add those 2, it will be about 6,000 planets / candidate planets that will be orbiting 3,000 stars, 2,000 stars, 1,000 stars. How many stars?
Something like that, yeah. It's worth noting, though, that In order to make this measurement, it's really helpful to have the time series observations that are very short. So something that I haven't mentioned yet is that there are two types of data that came from the Kepler mission. For every star, it took an image every half hour. And then for a subset of the stars, a much smaller sample, they measured the brightness every minute. And you need the 1 minute cadence observations in order to really unambiguously measure these spot occultations. Because as you can see, the spot occultations in this plot last of order 5 or 10 minutes. And so you need the 1 minute cadence data compared to the 30-minute cadence data where all of that brightness would be smeared out in time. So the number of short cadence targets, the number of 1 minute targets that have planets is in the, maybe in the 1,000 range. And the number that have obvious spot crossings in them that look like this system is 3. We could argue about 3 versus 5, but it's roughly 3. So there aren't very many that show these obvious spot occultations. There are many that could have marginal spot occultation observations. And that's one of the places where machine learning techniques might be really interesting to apply, because if you can pull out the signal and the noise, there might be a lot more to recover, because we do expect that stars are spotted. The problem is that most stars probably aren't as spotted as HAPI 11 is.
Thank you.
Yeah, and that's all I have prepared. I would love to take any and all questions that you may have.
Brett, I have a question about the histogram with the distribution of the spots that you just showed.
Yes.
It seems that there is an apparent asymmetry between the hemispheres.
Yes.
Have you any explanation for that? I mean, in the sun, it's more or less symmetric, more or less the same frequency of spots in the two hemispheres. In HAPI 11, I think it's significant. You have some apparent asymmetry.
That's right. So this question is fun. I love using this slide because I sneak it in as a trick to make people ask that question. I could have made this plot in a way such that the sun's hemispheric asymmetry would look equally significant. But I didn't, so that people would ask me this question. It turns out, depending on the 4 years that you choose to bin the solar observations on, occasionally the solar activity cycle starts in one hemisphere slightly before it starts in the other. And as a result of that slight asymmetry of when the hemispheres turn on, you get a slight asymmetry in the spot distribution. So what we're probably observing here is the activity cycle of HAPI 11 raging in the northern hemisphere and beginning in the southern hemisphere. It's hard to say that for certain because we don't have a long enough time baseline to really see it vary. One thing that we know is in our favor, though, is that the orientation of the star is not perfectly equator on. We're observing 10 degrees off the equator. Those 10 degrees actually make a difference and bias us towards measuring the southern hemisphere of the star. But it's the southern hemisphere of the star that has less spots in this plot. So we're actually biased against seeing the northern hemisphere spots, and yet we see more of them. That probably suggests that what we're seeing is real, and what we're seeing often occurs. The level of asymmetry that we see in this system is totally consistent with what the sun does.